Hello everyone, welcome to the today's session. As usual, we'll have this today's session on solving some sample problems for the basics of material engineering course. So today we'll be looking at nucleation and TTT diagrams. So let's begin the first question. So the first question is regarding ice nucleates at minus 40 degrees Celsius. So we know that ice to water that melting point is 0 degrees Celsius. So that information is not mentioned here. And it has a latent heat of fusion equal to minus 3 into 10 power 8 joule per meter cube. And it has a surface energy of 0.025 joule per meter square. Now we are supposed to estimate the critical radius. So to actually get to the critical radius, first let's understand what happens when the nucleation starts. Okay. So in general, initially everything is in liquid phase state. Okay. So everything is liquid. Now at the point where nucleation started, slowly around that nucleation site, a spherical will form which converts into solid. All the liquid in that sphere has turned into solid now. So as it grows, the solid sphere, at some particular radius, the growth will stop. So that is the critical radius. Where the free energy, rate of change of free energy with respect to that radius equals 0. So now we are supposed to estimate what is that radius. So as the liquid is converting to solid, there is a change in energy difference because of the conversion of liquid to solid. So that would be volumetric change. So that energy change due to conversion of liquid to solid would be 4 by 3 pi r cube into, so volumetric whatever per unit conversion, solid liquid to solid. And because the surface is forming, there will be energy due to the surface also. So that would be 4 pi r square gamma, where gamma is the surface energy, okay, per unit area. Now the total actual free energy that reduces from, because of the going from liquid to solid and due to the formation of this surface, will be the addition of these two. Okay. Now if we do this equal to 0, so the point at which this happens is the critical radius. Okay. Here that turns out to be, so derivative with respect to r for this would 3 r square. So 4 pi r square delta GV here plus 8 pi r surface energy is equal to 0. Okay. So this would give us 4 2 pi r. So r star, the critical radius is minus 2 surface energy by delta G, that liquid to solid conversion, the free energy. Now there is, because we are not given this free energy directly, we are only given the latent heat of fusion. So there is a direct relation between this free energy and latent heat of fusion, that is given as, so Tm is the melting temperature and T is the actual temperature at which nucleation starts. Okay, so then the critical radius directly would be minus 2 gamma Tm by delta Hf into Tm minus T. Okay, so this is the critical radius. Now the values which were given for water are, we know the melting temperature of ice 0 degrees Celsius, so 273 Kelvin, and the temperature where nucleation is at minus 40 degrees Celsius. So the temperature in Kelvin would be 273 minus 40. Okay. Now delta Hf, latent heat of fusion, is given as minus 3.1 into 10 power 8, and surface energy is given as 0.025 joule per meter square. So if you substitute this, the critical radius would be minus 2 into 0.025 into melting temperature 273 Kelvin by latent heat of fusion minus 3.1 into 10 power 8 into Tm minus T, so 40 degree 40. Okay. Now if you substitute all these values, you would get around 1.1 nanometers. So this is the critical radius for the nucleation for ice with these given conditions. Okay, 1.1 nanometers. So this way, this is we have looked at ice. Let's say if any metal, you are starting from melting point and then you are trying to get that nucleation. So similar way we can calculate for any metal also. So in the next questions we will see for a metal case. So here we are looking at titanium, a similar question. Melting point of titanium is given and it homogeneously nucleates at 1350 degrees Celsius, and latent heat of fusion is given as minus 1.7 10 power 9, surface energy 0.17, again critical radius we are asked. So directly, because now we know the formula for critical radius, minus 2 the surface energy into melting temperature by latent heat of fusion into the difference between melting temperature and the nucleation temperature. Okay, so that would give us minus 2, surface energy is given as 0.17 joule per meter square, melting temperature 1650 degrees Celsius, so we need to convert it to Kelvin. Okay, and then latent heat of fusion is given as minus 1.7 into 10 power 9 joule per meter cube, and then the difference between melting temperature and nucleation temperature, so 1650 minus 1350. Okay, so so 3 7 8 9 10 11 12 600 9. So if you solve this, let me calculate it. Minus 2 into 0.17 into 0 1923 by 1.7 E9 into 300. So you will get around 1.28 into 10 power minus 9 meters. So 1.28 nanometers. So this is the critical radius for titanium. Okay. So this way we can estimate for any metal, and you should be able to solve the questions in your assignments also. Yes sir. Yes. Free energy is maximum actually. Delta G will reach a maximum if you see the search slides. Okay, okay, okay. Yeah. So first is the conversion from liquid to solid. What is the free energy change that is happening when it is going from liquid to solid? R cube into delta GV. Yeah, that delta GV is for this liquid to solid conversion per unit volume. Yeah. Yes. So because previously liquid there is no surface. Now solid and liquid there is a surface between this. So because of that there will be extra free energy. So that part. Yes. So let me just check that again once. Maximum. Yes. Yeah, we are actually maximizing the delta G, total final delta G. Yeah. The free energy, this is free energy, so free energy should be maximum. Yeah. Yeah. This is the free energy. We are only talking about free energy. Yeah. Yes. So this direct relation is there between internal free energy and the latent heat of fusion in terms of melting temperature. This relation. So if you substitute all that, then you will get the critical radius in terms of surface energy and melting temperature and latent heat of fusion. So this formula only, first we did it for water, ice to water to ice, and then we are now doing it for titanium. Okay. So in the next question, we have a similar again, but here instead of asking critical radius, they have also asked what are the number of atoms found inside the volume of that critical size. So again we are given all the delta HF, surface energy, melting temperature, homogeneous nucleation temperature, and lattice parameter is given, and we are supposed to estimate number of atoms found in the nucleus of critical size. So first we need to estimate the critical radius and then see number of unit cells inside that critical radius, and if you know the crystal structure then we can see the number of atoms. Okay, so let's try to solve that question. So first, critical radius minus 2 gamma melting temperature by delta HF into Tm minus T. So this would give minus 2 into surface energy 0.255, melting temperature 1455, and delta HF latent heat of fusion minus 2.53 into 10 power 9. And then here supercooling value is given. That means supercooling value is actually the temperature, like how much it is lower than the melting point. So actually the difference is directly given. So when they say supercooling, so this is actually Tm minus T. Okay, so that is given as 320. So if we substitute all these values, then we will get the critical radius as, let me calculate it, 0.255 into 1455 plus 273 and 2.53 10 to 10 power 9 into 320. So you would get around 1 point, so you'll get around 1.088 nanometer. So this is the critical radius for nickel with the supercooling of 320 degrees Celsius and melting temperature of 1450 degrees Celsius. Okay. Now we need to estimate number of atoms inside this sphere of critical size 1.088 nanometer. So because we are given the lattice parameter, so let's see what is the spherical volume for this critical size. 4 by 3 pi r cube, right? The volume. Yeah. Now each unit cell volume would be directly a cube. Okay. Now number of unit cells inside nucleus of critical size would be what? So in this entire volume, how many unit cells we can fit? So it's just a ratio of 4 by 3 pi r star cube by a cube, right? So this number of unit cells we can fit, and nickel is actually an FCC crystal structure. So number of atoms per unit cell is 4. So total number of atoms inside the nucleus of size r star would be, so 4 into 4 by 3 pi r star cube by a cube. Okay, so let me calculate this. 4 into 4 into pi into r star. So we got 1.08 nanometer. So 1.088 whole cube by 3 into 0.36 nanometer. So you will get around 462.52 number of atoms. So approximately 462 to 463 atoms. Okay. So is this clear? So first we are actually supposed to estimate the critical size of the sphere and then calculate the total volume of the sphere, and because we were given the unit cell parameter, we can estimate how many number of unit cells will it can fit in that sphere. From then each unit cell will have n number of atoms based on the crystal structure. So then we can estimate the total number of atoms inside the sphere. Okay. So hopefully this is clear. Yeah. So let's move on to the next question. No. Yeah. So R we have to estimate. So this is the direct formula for R, critical radius R. In terms of surface energy, melting temperature, latent heat of fusion, and melting temperature, nucleation temperature. Yeah, you can refer to the video at the end, and yeah, we have discussed how that formula comes in the first question. So let's move on to the fourth question. Now, during isothermal phase transformation, fraction transformed is measured at two different times. So at 75 seconds, only 0.11 fraction has transformed. At 150 seconds, 0.37. Now fraction transformed in 300 seconds is. So here they didn't give any law which it follows. In general, this is supposed to follow this law. Okay. So the fraction in terms of time usually follows this law. So now this k and n are the unknowns. Okay. So to estimate these two, because we have two data points, we can easily estimate. So let's write it this way. E power minus k t power n can be written as 1 minus f, right? Now let's take ln on both sides. Then this would be minus k t power n into ln of 1 minus f. Okay. Now if you substitute case 1, 75 seconds and 0.11 fraction. So minus k t1 power n ln of 1 minus f1. And if you do second option, minus k t2 power n ln of 1 minus f2. Now if you do the ratio of 1:2, so minus k t1 power n by minus k t2 power n is equal to ln of 1 minus f1 by ln of 1 minus f2. So this k gets cancelled. So we will get t1 by t2 whole power n is equal to ln of 1 minus f1 by ln of 1 minus f2. So now again I will take ln. So this would become n ln t1 by t2 is equal to ln of 1 minus f1 by ln of 1 minus f2. True, correct? So then n would be ln of by ln of 1 minus f2. by ln of T1 by T2. So now this way we can estimate n, because we are given already the values of f1, f2, T1 and T2. So let's substitute them. T1 is 75, T2 is 150, and f1 is 0.11 and f2 is 0.37. So if you substitute that, n would turn out to be, let me substitute these values. So log of 1 minus 0.37. So n would be 1.9873. Okay. Now we know n. So how can we get back t again? So let's substitute this n in the first equation itself. So minus k 75 power n is equal to ln of 1 minus f1, which is 0.1. So this would give k as okay. So minus log of 0.89 by 75 power 1.987. So you would get k as 2.1885 into 10 power minus 5. So now we got k and n, right? The constants in the temporal variation of the fraction. So the final equation fraction would be 1 minus e power minus k into t power n. Okay, this will be the final equation. Now we are asked to what is the fraction in 300 seconds. So t equal to 300. So f would be 1 minus exponential of minus 2.1885 minus 5 into t power something. So 0.84. Okay. So this way, if you are given at any two instances at any two different times, we can estimate the fraction transformed in any other time. We can first estimate the constants in the equation, and then the fraction at a different time. Okay, so this is for isothermal phase transformation. This equation you can use. Okay, so basically first we try to estimate the constants in terms of given known values, and then use that to estimate the actual equation, and then we substitute the time which we are supposed to estimate. Okay, hopefully this is clear. So next we have TTT diagrams. Okay, so is this clear till now, how to estimate this fraction and yeah, and this latent heat of fusion and critical radius? Yeah, so if time is there, I will cover that critical radius again, because today we don't have that many questions anyway. Okay, so yeah, so this is a TTT diagram, a very rough diagram. So in the question is, name the microstructures obtained after heat treatment of ejected steel in the TTT diagram. So these are the four paths of cooling someone has followed. Now we need to estimate the final microstructures which will be existing in this PQRS. Okay. So does anyone have any idea what would S be? Yeah. So actually in this diagram, anything below this line, if you are directly coming from austenite, it will turn to martensite. So because S you are, and to the left, this will always be austenite. Okay. I think this green is not clearly visible here. Yeah. To the left of this graph, it will be austenite anywhere. Okay. And austenite is unstable at room temperature. So whatever austenite is present, as you cool down less than this temperature, whatever this, or come down to room temperature, austenite will always turn to martensite. Okay. So here you are always in the austenite state only, and then came to directly to martensite state. So this would be martensite. Okay. And to the right of this, you have at this slope, above you have perlite and below you have bainite. Okay. So this perlite and bainite are stable. So if you get to these states and then cool down, you will perlite will stay like perlite and bainite will stay like bainite. Okay. Yeah. So from the neck region. Yeah. Okay. So because you are at this R, so what would R be now then? Yes. Yes. So R would be bayonet. So basically, if you are going this way, horizontal lines, that means you are allowing the material to transform slowly. So when that happens, austenite will slowly, as you give enough time, it will convert to bayonet. But if you stop in the middle and then come, so let's say this case, and then suddenly cool from here, then what will happen? Yes. So there will be a fraction of bayonet plus fraction of because whatever austenite is there at this state, that will completely convert to martensite. But because bayonet is stable, bayonet will stay like bayonet only. Okay. Yeah. So then what would be Q? Yeah. So in perlite also there is a differentiation. Close to the necking, the perlite will become finer and finer. Okay. So and far away from the necking, it will be coarse. So this would be the finest perlite. So Q you can say like middle fine or fine. Okay, based on the options you are given. So as you move from here to here, it will become finer. Okay. So this would be P, Q, R and S. So again we have similar questions. So this will be repeated again, and maybe you can understand it better. So let's see the next question. Yeah. Now they have given us 4 curves again, and which curve will produce 50% bayonet? So that is the question. Okay. So what would S be? S 100% martensite, right? Yeah. R, mm, actually no. See, it depends on the rate of cooling. If you are suddenly changing, these graphs are supposed to be suddenly changing things. So you are not allowing bayonet to form. So this would also be 100% martensite. But what about Q? So in Q, you are allowing bayonet to form from martenite. Okay. So at this point, there will be 50% bayonet and 50% arsenite. So this would give you 50% martensite plus 50% bayonet. Yes, if you are doing instantly, then it doesn't. You are not allowing for arsenate to convert to bayonet. Yeah. What about P? Yes. Yeah. So because till here when you came, it will be 100% suddenly you came, so arsenate, but then you are letting it cool down. So all the arsenate will convert to bayonet. Letting it at the temperature or allowing it to transform. Okay. Mm, I don't think there is any difference. It's just fast cooling, so both of them will might give 100% mark side. But I'm not 100% sure actually because this is not instant cooling. Uh, think so because once bayonet has formed, will it revert back to austenite? No, yeah. So I think austenite to convert to bayonet, you need to let it cool down a little bit, right? Yeah, like I transform it a little bit. So I think this would be 100% martensite only. Or I'll check again and update in the final notes. Okay. Uh, I didn't get you. What? Yeah. Okay. Yeah, this line. Yeah. Okay. Okay. Yeah. Yes, I think so. Yeah. So this should have some bayonet. I am thinking because it's not very fast cooling. Yes. Yes. But because the question is 50% bayonet, only Q would give for sure 50% bayonet. Yeah. Yeah. So yeah. Okay. So let's move to the next question. Yeah. Again TTT diagrams only. Now we were given this step by step temperature changes and we are supposed to estimate the microstructure. So in case 1, 900 to 650 sudden cooling and held for 1000 seconds. So 900 is above somewhere and then 650. So somewhere here sudden cooling. So straight vertical line and held for 1000 seconds. So I didn't write anything. It's just a vertical line and then waited till 1000 seconds. Okay. So this point. So this is 650. 900 to 650 and waited till 1000 seconds. So what will be the microstructure for this? No, this is above this neck. Yeah. So this would be 100% perlite. So case 1 would be perlite. Now in case 2, 900 to 500 sudden cooling held for 5 seconds and again sudden cooling to room temperature. Okay. So 900 to 500 would be suddenly like this instant cooling. Okay. And then only held for 5 seconds only. So okay. So this is 5 seconds and then sudden cooling to room temperature. So yeah, so what would be the structure for this? Yes, yes, because you are slowly doing, no, so you are allowing it to transform. So it will have 50% because you are in the midline. So this point will have 50% austenite and 50% bainite, and because you are below the neck. So and then you are suddenly cooling it. So all the 50% austenite will become martensite. Plus 50% bainite. Okay. This is case 2. This is case 1. Now case 3. 900 to 700 sudden cooling held for 100 seconds, and then from 700 to 300 sudden cooling again and held for 10 power 4 seconds. Okay. So let's see where this is. 900 to 700 first. So 900 to 700, this line till here, and then 100 seconds. So 100 is this line. Okay. So now we still have fully austenite only, right? Because we are still to the left side of the curve, red curve, and we have suddenly cooling from 700 to 300. So we are suddenly cooling till here, and held for 10 power 4 seconds. So now 100 plus 10 power 4, so that would be actually somewhere very close to 10 power 4. Okay. Yeah. And yeah, so what would be the case now? Yes. Yeah. So actually that is it for today. We have only this many questions only. So yeah, because we are instantly cooling, right? So there won't be any perlite. It will, all the austenite will convert to bainite only. What do you mean by that? This point, huh? Oh, this one. That I'm not sure. Maybe if you go to even longer time, it might touch. Yeah. Yeah. Okay. Okay. This point. Yeah. Okay. So first question. Huh? Yeah. 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 So I'll repeat them. Others you can log out now. That's it for today. Yeah. Okay. Yeah. Okay. So let's look at first question again. Uh, so here we are talking about nucleation. So you are in. So this is actually negative. So ice. Okay. Okay. Water to ice formation here, and we are supposed to estimate the critical radius. Okay. So maybe this is a bad example. So actually when liquid is forming, turning into solid, there is a change in free energy, right? So let that free energy be delta GV per unit volume. And when it is forming a sphere of radius r, so the total change in free energy due to the formation of solid from liquid would be volume into that free energy change per unit volume, right? Now, when liquid that solid is forming, there is also a surface getting created between solid and liquid. So because of that, there will be extra surface free energy also. So that is defined as 4 pi r square into gamma. So gamma is surface energy per unit area. So now there are two free energies. So the total free energy would be volume of sphere into volumetric free energy of conversion from liquid to solid, and surface area into surface energy per unit area, right? So uh, let's so this total free energy actually initially increases and then decreases. So when it reaches maximum, that is called the critical radius. Okay. So like for the reactions to happen, free energy should be as high as possible. So then the reaction can freely happen. So for this critical radius, to get this point, we are just simply derivating this total free energy with respect to r and then equating it to 0, because at the maximum the derivative would be 0. Then we will get this critical radius in terms of this surface energy and volumetric energy of liquid to solid. Okay, and this delta GV is directly related to latent heat of fusion and melting temperatures in this way. Okay, so substituting this, we will get critical radius in terms of surface energy, melting temperature, difference between melting temperature and the nucleation temperature, and latent heat of fusion. Okay, so this is the formula which we use to, in this case, estimate the critical radius, substituting everything. So similarly, we have question 2 also. In the case, we have titanium. So similarly, we estimate the critical radius. And in third question also, we are supposed to, instead of asking critical radius, they went one step ahead and asked what are the number of atoms inside the sphere, nucleus of critical size. Okay. So first we estimated the critical radius. Yeah. So the derivative of this would be 4 by 3 pi into 3 r square delta GV, plus this would be 4 pi into 2r into gamma. Okay. So, yeah. This negative, this delta GV is actually negative, so it takes care of that. Yeah. So delta HF is negative, so delta GV would be negative. Okay. So yeah. So in this question, first we got the spherical volume after estimating critical radius, and then we know the unit cell volume. So then we got the number of unit cells inside that sphere by directly the ratio of the volumes. And if you know the crystal structure, then we know the number of atoms in unit cell. So then we can guess the number of atoms inside that nucleus. Okay. Yeah. So that's it for today. We'll meet again next week. Same time. We may have mostly or may not. I'm not exactly sure. I'll check with the team, and if there is a session like that, you will get an email. Yeah, some all the topics, one question each. Yeah. Yes. Yes. No, no, no. No. Yeah, if it is a multiple choice question, you will in the assignments at least you are able to see different kind of setting the options, right? So also it could be there. Final thing also it could have questions like that. Yes, yes. There would be numerics, there would be direct single option, there will be multiple choice options. You should expect every kind of question. No, it's like, see, for this question, let's say, the answer would be given as from 455 to 475. Anything in between that, it will be a correct answer. So if you get in the close range, it would be fine. You don't have to give the exact answer as 462. Okay. Yeah. So even if you make some numerical mistakes, that would be accounted for in the solutions. Okay. So thank you everyone.